Spartan fans, it is time to look at more limits involving infinity as well as continuity. Okay, so go ahead and plug in the sign of 2x over x into your calculator. And when you graph it, you should get something like this. And you know what? It looks very similar to the sign of x over x. It looked very similar. So in this case, if I ask you the limit as x approaches 0, so the exact value is undefined. The f of 0 is undefined. But that doesn't mean the limit doesn't exist. So the limit, if you look at your calculator, the limit of this function as x approaches 0 is equal to 2. So you can tell 1 by looking at your calculator, but let's also tell by looking at tables, your ability to use the calculator obviously is going to be critical. So I'm going to do second table set. Now I've changed my calculator since the last video, so mine's a little bit different. Oops, let's fix that. Okay, so there we go. So I happen to be at -49, but I'm going to say 0. And I changed my table to 1. And notice it says that the exact value, error, but from the right and from the left, if you look at the graph, it is clearly approaching 2 from both directions. But what about the limit of this graph as it approaches infinity from the right and from the left? So that would be negative infinity and positive infinity. So infinity from the right of the function and infinity from the left. My apologies. There's no such thing as infinity from the right. We just want to look at positive infinity and negative infinity. Sorry, I'll write that out. Okay, so let's look at the calculator and the table. Just so an FYI, it is okay to write f of x. You don't have to continually rewrite sine of 2x over x, but so I wrote f of x instead. Totally okay. You need to have something though, either an equation or the function. Okay, so I'm going to go back to my graph, and what's happening as x approaches infinity? What's happening to the value of the function as x gets large, 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 large? And it appears that it's approaching 0. And the same thing, this appears to have y-axis symmetry. So as I'm approaching negative infinity, it looks like it's approaching 0. So how can I see that on my calculator? I'm going to my table set. My table is by ones. Yeah, that's going to take me a long time to get to infinity, right? If I'm going by 1. So how about we do something like, I don't know, 100. Go to your table. And you can see 100, 200, 300, etc. As you scroll down, hopefully you have your own calculator. As you scroll down, this is clearly approaching 0. I'm going to try to zoom in. Not quite sure what's up with the camera, why it's not quite focused, but it is definitely approaching 0. And if instead of going in the positive direction, I go in the negative direction, I go the other way, you should be able to see on your calculator that the graph is indeed approaching 0. We are going to be using the calculator quite a bit. So when the problem says, evaluate the function graphically, plug it in. Let's look at something like, how about the function of x over x plus 3? Now, of course, what we really care about is -3. Yeah, so let's review from Algebra 2 Honors. So we have vertical asymptote at x equals -3. That's really what we care about. So the f of -3 is undefined. The f of -3 is undefined. Then we can find, let's see, the x-intercept is the same as the y-intercept, which is the origin. Same. Then the horizontal asymptote is going to be at y equals 1. Divide the lead coefficients. So we do have our calculator, so let's just go ahead and plug it in. Plug it into your calculator, do a Zoom 6, and here you go. So it appears that as x approaches infinity, y is approaching 0. And as x approaches -infinity, y is approaching 0. Guess what? We already knew that based on our horizontal asymptote. So the limit of this function as x approaches infinity is equal to 0. And the limit as x approaches -infinity is also, is also equal to 0. So let's use this as an opportunity to talk about continuity. We're going to look at this as continuity. So I'm going to ask you, is the function continuous at x equals -3? And the answer to this is going to be no, and it's going to be no for several reasons. Okay. So is f of x continuous at x equals -3? Okay, the answer to that right away is no. There's an asymptote at -3. There's an asymptote at -3. Well, wait, great, there's an asymptote, but what does it mean to be continuous? Okay, so the non-mathematical definition is, can I draw the whole graph without picking up my pencil? Well, I have the graph on my calculator. Just here. Could you draw this whole graph without picking up your pencil or your marker or your highlighter or your crayon, whatever? And the answer is, of course not. You can't. You have a branch, then you have to pick up your pencil and you have to draw the other branch. So that's a very non-mathematical definition of what it means to be continuous. So let's talk more about what it means to be continuous mathematically. Okay. The answer is no. So there's a vertical asymptote. So as soon as you have an asymptote, we have issues. Let's look at the limit. So let's look at the limit of this function as x approaches 3 from the left, -3 from the left. Let's look at the limit of the function as we approach -3 from the right. And you know what, let's just do a really quick graph since we're here. There's a rough sketch. So I look at this and I say, okay, the left-hand limit exists. As I'm approaching -3 from the left, my graph is approaching infinity. And my limit as I approach -3 from the right is -infinity. So at asymptotes, for asymptotes, your graph either approaches -infinity or infinity. I'm pretty sure that was in the last lesson. And as I approach, as x approaches infinity, large values of x, y approaches 0. And as I approach -infinity, large negative values of x, I approach 0. Okay, well, we have limits. So just because the f of -3 is undefined doesn't mean the limit doesn't exist. So we've got a left-hand limit, great. We have a right-hand limit, awesome. The overall limit does not exist because they're not the same. The overall limit does not exist. Okay. What about 0? What about 0? This graph is not continuous at -3. We got this asymptote. But what about, is it continuous at 0? The f of 0. So my function is x over x plus 3. Is the f of 0 defined? And the answer is yes. The f of 0 is 0. What about the limit as x approaches 0 from the left? So the limit as x approaches 0, I'm approaching 0. How about the limit as I approach 0 from the right? So as I'm approaching 0 from the right, the y value is also 0. If the left-hand limit is 0 and the right-hand limit is 0, then we say the limit exists and it's 0. This function is continuous, and here's why. The exact value exists, it's 0. The left hand and the right hand exist, which means the overall exists. And not only, right, they all are the same, they all have the same value, in this case 0. So we say that this function of x over x plus 3 is continuous at 0. And of course, we'll do a definition. Let's look at an overall definition of continuity. So, sorry, that point. Okay, so you're given a point at x equals c. The function is continuous at c if the limit as x approaches c of the function is the same as the exact value of the function. So you have some value c. If the limit as x approaches c of the function is the same as the exact value, then we say it's continuous. But here's an issue. If the limit as x approaches c exists, this means that the limit as x approaches c from the left of the function is equal to the limit as x approaches c from the right of the function. So there's like a subset of that. The limit has to equal the exact value. And then in order for that limit to exist, the limit from the left must equal the limit from the right. How is this going to happen? No holes, no asymptotes. How about vertical asymptotes? At that point, if there is a vertical asymptote, the limit exists, but not the exact value. If there's a hole, the limit exists, but not the exact value. So it has to be what we just call a smooth curve at that point. Well, sure, this is a nice smooth curve here on the left or the right. This is a nice smooth curve on the left, but there's this asymptote in the middle. So this function is not overall continuous because there's a break at x equals -3. It's got individual continuity, but not overall continuity. Okay. Let's take a look at some other functions. What happens with the f of x equals x plus 3 over x squared minus 9? This function is discontinuous. And you know that right away because there is a denominator. Denominators mean asymptotes, boom. So this particular function is going to be continuous at some places, but not at others. So let's reduce this, and that would be 1 over, how about 1 over x minus 3? Vertical asymptote. This function is not continuous at x equals 3. X equals 3, 0 on the denominator, right? Old news. Oh, but what about positive 3? Or sorry, negative 3. We already talked about positive 3. Let's look at negative 3. Cool. Well, at negative 3, we're all good, yeah? At x equals -3, we get, how about -1/6? Yeah, awesome. So this function is continuous at -3. Of course it's not. It's a hole. These holes come back to haunt you from last year. This is called a removable discontinuity. This has two what I always call bad values. If x is 3, no can do. And we already talked about that. And if x is -3, no can do either. The issue is it was a problematic value to begin with, and then you took it out. It's called a removable discontinuity. You have removed the issue. It is still the graph, even though it appears to be continuous at -3, it is not. Discontinuity. I love that word. This is a hole. So this graph is discontinuous at, it is discontinuous at x equals 3, which presents itself as a vertical asymptote. And it is also discontinuous at x equals -3, which presents itself as a hole. Two types of discontinuities. There's not a smooth curve. All right, let's do one more. We'll have more practice with this after spring break. Ooh, how about something like the f of x equals the cotangent of x. Okay, there's cotangent. So keep in mind that cotangent theta x whatever is undefined asymptote where the cosine is 0. Sine, not cosine. So the sine is 0 at 0, pi, 2 pi, 3 pi, and then going the negative direction as well. So this graph is continuous everywhere, right? Like I drew a nice smooth curve, but I had to pick up my pencil. And I drew a nice smooth curve and I had to pick up my pencil, or in this case, my pretty blue marker. So the cotangent is continuous at all values of x. X not equal to integer multiples of pi. So we could say it is continuous at pi over 2. Let's say it's continuous at 3 pi over 4. It's continuous at 11 pi over 6. As long as it's not an integer multiple of pi, we are good to go. So there's a basic introduction to continuity, and we will look at that more in the next lesson.